All right, so thanks for the invitation. And I'll start by a disclaimer. So I'm actually ill. So if I end up saying that Google DeepMind's RL technology is better than ours, then probably I have overdosed on cough medication, right? So who of you knows reinforcement learning? You ever heard of reinforcement learning? Cool, all right. So can I walk? Yeah, all right, cool. So let us start by some motivation on why anyone should care about reinforcement learning. So if we are to consider any of the following applications, say self-driving cars, a finance application, we're trying to design some trading strategies, logistics, where we're trying to have some warehouse allocation, for example, or reducing estimated time of arrivals, robotics, or even video gaming. Though these problems look different at a high level, they actually share a communality. And that communality is there's an agent performing a sequence of decisions. So was it the self-driving car or the finance agent? They're trying to make a sequence of decisions. And they're making this decision in an uncertain environment. So we cannot pre-program all the potential cases that this agent would face up front. And that is happening in presence of other agents. Now, not incidentally, this is the story of Prowler. So these are our three research teams. So agent performing sequence of decisions, that's reinforcement learning, and that's the team I'm leading. Uncertain environment, that is concerned with forecasting and predictions, and that's the team James Hansman is leading. And the strategic aspect of interactions is the multi-agent systems research team that is led by Enrique Munoz. So to solidify reinforcement learning, let's just give a brief introduction on it, and then we'll move fast over this because you guys know it. So we have an agent and we have an environment. The agent talks to the environment by taking an action in that environment, to which the environment responds by a successor state and some reward function. So assume I'm the agent and I'm trying to reach the door up there. So I'm in this state now. I decide to take a step forward, so I move forward. Then my state changes, and if I get closer to the door, then I get a positive number saying, oh, I'm closer to the door, that's good. Otherwise, I get a negative number or no reward at all saying, yeah, that was a bad move. As time goes on, I interact with this environment over and over again along a horizon, along a length, like a time length. So I start here, I move there, and so forth. And then I collect this set of traces, which are formed of state, actions, successor states, and rewards. And then my goal is to learn a policy. You can think about it as an action selection rule. So this is like a box, and in that box you give it some state, it gives you some action. So this policy should learn how to pick the right actions for me to reach that door. So as I gather more and more experience, I start updating my policy over and over again by enforcing the good stuff and unenforcing the bad stuff. That's where the term reinforcement learning comes from. Please note that was it the agent driving, or was it Mario in a computer game, or was it a robot trying to cook for me something in a kitchen? This idea is the same across all these different domains. There are always an agent doing a sequence of actions in order to maximize its reward, to maximize the good stuff it can do. So if I'm able to crack this problem, then there's a widespread potential applications that we can do using such form of AI. So I'm sure some of you have heard the term deep Q networks, which was maybe the major success in reinforcement learning over the past couple of decades. In deep Q network, the agent observes the state of the environment to be just a snapshot, an image of that environment. For example, Mario being here. And then that is passed through a very complex function, which is typically a convolutional neural net. And that is mapped through that function to low-level Q values, i.e. low-level actions. So this quantifies how good is the action that the agent will execute, given that I have seen such a snapshot of the environment. So this bar graph you see there is from DeepMind's Nature paper, where they applied this type of idea to ATARI games, and they showed that using this idea and learning over and over again with millions of interactions with that environment, you can actually do better than humans in some of these games. Now, such an idea has also been generalized to robotic-like scenarios. So it's, again, the similar idea. The robot observes through the camera the environment, and then that is mapped through a very complex function to low-level torques or continuous actions in this space. So that has been pioneered by Sergey Levine and Pierre Abel from Berkeley, and these are examples of this being applied to like a PR2 in a simulation environment trying to make some sort of a coffee or something. Now, though successful and impressive, current reinforcement learning technology takes tens of millions of environmental interactions to learn something useful. So that agent and that environment, for it to learn a good policy, it has to talk to that environment over tens of millions of times, and then it learns something useful. Now, clearly, this does not scale to what we want to solve. I can't have my agent commit tens of millions of mistakes before it figures out a rewarding strategy in finance. I don't want to lose all my money, right? So our goal is to try to scale reinforcement learning to have it data efficient and applicable to industrial problems. We want the learner to learn not from millions of interactions, but actually from tens of interactions with the environment. What I'm going to present next will show how we were able to make reinforcement learning much more efficient, and when I say much more, it's 3 orders of magnitude better than current state-of-the-art techniques. So for us to understand how we achieved this milestone, we need to understand what is being done wrong in current reinforcement learning practices. To illustrate, consider this maze. So the goal in here is that we have this robot represented by this blue dot here, and that robot has just to navigate this maze for it to arrive to the goal position depicted in red up there. The correct path for that robot to take is that bold line that we show with this blue column. All the dotted lines are potential exploration states that that robot can visit. Since reinforcement learning is learning by trial and error, you can clearly see that this simple problem requires tons of interactions for it to, by luck, visit that path depicted in bold there over and over again for it to learn something useful from it. You, however, looking at this maze, you never solve the problem in this way, right? What you do is you abstract this problem into 2 levels of complexity. You say the first level of complexity is depicted by a hierarchical structure of which door I should exit and which door I should enter, right? That's how you think about this maze. You say, you know what, I need to exit room 1, I need to enter room 2, room 3 in order to achieve the goal. You never think in low-level state representation. So if I am to go outside, I don't think I'm in X, Y, Z and I walk there. I just have in my mind a plan, right, that says I need to go up the stairs, exit the door, and so forth. Now, what we want to do is we want to enable such a hierarchy inside reinforcement learning to decompose the task complexities. So we want to have a task description, which is very simple to solve at the high level. And that will allow me to decompose this big problem into smaller chunks, easier problems, which I can efficiently learn. Please note that this goes beyond mazes. This example I just described goes beyond mazes to ATARI games as well. This game here is called the Montezuma's Revenge game. This is the Harvest ATARI game. So on that bar graph that I showed you from DeepMind, there's the other graph that I didn't represent. And the Harvest game where you get 0% learning is this Montezuma's Revenge game. In here we have this red dude, and this dude has to go down the ladder, down over the road, above the sub, get the key, go back, and then walk in one of the doors. You can clearly see, so this is the result of running deep Q networks on this problem. After 15 million interactions with this environment, you can clearly see that it's doing nothing useful. It's just doing random stuff, killing the agent over and over again, repeating the episode. That's clearly not working. So having described the first level of complexity, which I like to call the task level complexity, there's another level of complexity inside reinforcement learning that plays a role, and that is the agent level complexity. So far, I have described my robot to be a dot, where that dot can go back and forth, up and down, as I order it to do. But imagine that dot was actually a droid. It was a complex droid, where even if you gave it the right path to follow, there's a lot of coordination that needs to happen between its mechanical and electrical systems to even take one step forward. So even if I tell the droid, look, the task level complexity is like this, that problem is still difficult because it has to coordinate throughout its body for it to even follow that path that I gave. So what are others doing? They're taking these two levels of complexity, which we just call the task level and the agent level complexity, and now they're passing it through a very deep network, end-to-end learner, deep architecture, and they're trying to have these networks grow such that you can decouple these two levels of complexity and learn something useful from it. Please note that as I interact more and more with the environment, if I did one mistake, then my mistake gets more and more convoluted. And then I end up with even a harder and harder problem to solve. And that's why this solution is clearly inefficient, and it requires networks to grow more, and we need more and more data and make things more and more data hungry. And this is something that it will never apply to any industrial application. What we do, on the other hand, is we try to divide these two levels of complexities. So we consider the task level complexity versus the agent level complexity. We modularize the solution by creating hierarchies for each of these different levels. And then we try to collate them back together in order to solve the original problem. So I'm going to give two examples of how we do that next. And I'll be happy to take some questions towards the end on this. So the first thing we developed is something called divide and conquer for these different task complexities. What we are going to do, remember my maze problem, right? So what we're going to do now is we're going to decompose this maze into two problems that talk to each other, right? We will have a high-level problem depiction, and we will have a low-level problem depiction. Please note that the high-level problem depiction is not manually designed. Our agent is capable of discovering this high-level depiction. We can discuss that offline. This high-level depiction is supposed to give me the plan that I need to use in order to solve this problem. As you see, this is a very small NDP, right? It's a very small problem of 6 states, or even higher. But that's why I can learn this really very fast, using very old reinforcement learning techniques, like tabular Q-learning, for example. Once I've got that, now I'm going to guide a low-level agent so that it solves smaller chunks of the problem, so they collectively solve the big problem faster. So what I'm going to do is I'm going to have my agent start here. Then it's going to talk to the high-level agent. Ask the high-level agent, hey, where should I go next? Then the high-level agent will give it a sub-goal for it to reach. And then I will learn this small chunk of the problem so that I can go from this part to this part, not worrying about the overall problem. As time passes, then I will pick more and more of these states from the high-level agent, and then I learn a sequence, smaller chunks of policies or controllers that will take me from here to here, here to there, and so forth. Once I collate these together, now I'm able to solve the big problem much more efficiently than having one humongous DQN that is capable of dealing with this maze. So this should be much more efficient. By now, you definitely don't believe me. So what we're going to do is we're going to apply this idea to Montezuma's revenge. What you see on the right side is Prowler. So this is the idea I just described. You can see that our guy is capable of getting the key and then jumping over the skull. It gets stuck at the ladder for a while, I don't know why, but then it solves the problem. And then it's able to open that key. So this result is gathered using 900,000 interactions with the environment. Please note, 900,000 is not a 10 million, and it's not even a million, it's less than a million. So we were able, using this principled approach, to scale reinforcement learning to solve the first room of this game using only 900,000 interactions with the environment. That is the result you saw on the previous slide as well. So that's DQN with 15 million interactions with the environment. So given that we are now capable of handling task-level complexities, and though that the numbers are better than before, so 900,000 is better than 10 million, this is still not the number we're looking for, right? 900,000 is good, but we want tens and not 900,000. So now let's try to handle the other level of complexity of the problem, which is the agent-level complexity. What we're going to do is we're going to allow our agent to learn about itself using model-based reinforcement learning. So what we're going to do is we're going to allow the agent to understand the effect its actions has on itself and on the environment using probabilistic models. Given that we have a great probabilistic modeling team, then we should be able to crack this problem, right? So let's look at that. To illustrate the idea, consider the following simple benchmark in reinforcement learning, right? So this is a benchmark which is called the cart pole benchmark. I'm sure a lot of you have seen this before. So here we have a pole, and that pole is attached on the cart, and the cart can go back and forth, right? And your goal is to balance the pole in the top right position. We want to try to do that from images, yeah? So we don't want to do like 4-dimensional representation. We want to try to handle high-dimensional representation, but by doing model-based learning. What we have done is we have developed a probabilistic model, which is called the Gaussian process state space model. And that is capable of abstracting salient features inside these types of images for us to learn the dynamics of this environment. So we have y0 up to y3 here are different snapshots of this environment. x0 up to x3 are these latent representations that we're looking for. So these should be the salient representations. And from x to y, we have a complex mapping because x is low dimensional and y is an image. So we have here a deconv net, right? And what guides the dynamics in the latent space is the Gaussian process model, right? So why did we use the Gaussian process model? Partly because Carl Rasmussen is our chair. And the other reason is because they're very efficient in low data regimes. So applying this to this problem, what you see down there is the reconstruction. What you see up there is the ground truth. So you can see that our model is actually capable of capturing the intrinsic dynamics inherent in these sets of images that we have seen, right? And please note that this result we got using only 160 data points. So this is the first time anyone is able to train a deconv network like this with something less than thousands, tens of thousands of data. This is 160 data points. So our probabilistic model, our principal probabilistic model, was able to regularize our network in such a way that it extracts only the relevant features. And let's discuss this offline if you're interested in it as well. Please note that this result has been published in NIPS last year. And now what we're doing is we're carrying this to reinforcement learning. So now this is the model learner, right? So it learns the saliency inside my images. So now let's put it back in reinforcement learning and see what happens. So let us devise the following reinforcement learning algorithm. The first step is we will start with some random policy or random action selection rule. That random action selection rule will talk to the environment, and then we will gather some traces. Let's now, from these traces, use our probabilistic model in order to train a surrogate environment, not the real one, but something that we think represents the real environment. And then let's use that for us to do policy updates through reinforcement learning. So what we're going to do is we're going to have traces gathered. We're going to train our model, the one I just described before. And then we're going to update our policy. And then we're going to repeat this process. So we're going to go over and over again through this. The idea is that this should allow us to learn faster with lower number of interactions with the environment because we created a surrogate environment. We're not dealing with the real environment anymore. Now the tricky part is how can you get your surrogate environment to be accurate, right? And that's something we're working on. But in these types of robotics problems, it seems to be working so far. Now, how would we get it to generalize? That's our second step. So we're trying to mix model-free and model-based together. But for now, let's just try this on our simple problem and see what happens. So what you see here, sorry. What you see here is a result running this idea I just described on this problem of this carpal. On the x-axis, you see episodes. What are episodes? Episodes are the number of times I interact with the environment. On the y-axis, you see rewards. So the higher, the better. These are rewards. These are my learning process. If I get higher rewards, then I'm doing better. Please notice that the x-axis is logarithmic scale. You see three graphs here. These two graphs are from OpenAI and DeepMind. So anyone who knows policy search, these are called PPO2 and TRPO. And sorry, they're both from OpenAI. And the orange line you see there, that's from DeepMind. So the idea is that DeepMind did the same thing like this one, but used a neural net instead of our probabilistic model. So this gives us a comparison of how well is our probabilistic model doing compared to using a neural net in such type of environment. These results show that you can actually learn this system in maybe 2,000. So that number here is about 2,000 interactions with the environment. What you see here, that's our result. And the number up there is 15. So this was able to achieve the highest reward of 18 in this case, in 15 interactions with the environment, as opposed to 2,000 interactions with the environment for the state-of-the-art techniques. So we're clearly on the right path, and this is a 3 orders of magnitude reduction compared to TRPO, PPO, and even neural net-based models. What we're doing now is we're extending this to higher dimensions, higher, like more complex robotic systems, but also we are handling partial observability. So in any reinforcement learning problem, we assume that the state ST is fully determined for us. But anyone in industry doing reinforcement learning understands that this is a false assumption. There's always partial observability inside my state representation. Interestingly, our model can also handle partial observability, and in fact, it can learn such a problem when we omit giving it the velocity of the cart and the velocity of the pole in 7 interactions, in 7 episodes, which is kind of very cool. So this result is not here, but we just got this result yesterday, so it's pretty cool. So now, all this is available in a platform we are designing called Decouple. So this is the platform of Prowler to do decision making. It combines reinforcement learning, probabilistic modeling, and multi-agent systems together. And all these technologies that I just described, and many others from the other teams, are already available in Decouple. And that allows us now to use reinforcement learning, probabilistic modeling, and multi-agent systems in real industrial problems, as we are doing with 2 applications in logistics and finance. Thank you.